Chapter 7: Gases, Liquids, Solids, and Phase Diagrams. Section 7.6: The Phase Rule. The phase rule states that in a phase diagram, F equals C plus 2 minus P. F is the number of degrees of freedom. This P is the number of coexisting phases. C is the number of chemically independent species. Let's look at this variable F. F is the number of the degrees of freedom in a phase diagram. For example, pressure, temperature phase diagram, we have two variables, pressure and temperature, and thus in general we have 2 degrees of freedom. However, if you are looking at any coexistent line between two phases, there is only 1 degree of freedom. And also, if you look at the triple point, it contains 0 degree of freedom because you are not allowed to change the value of pressure or temperature at the triple point. Now, P is just the number of coexisting phases. If you have only a liquid phase or only a gas phase, P is 1. Along the coexistence line, there are 2 coexisting phases. At the triple point, P equals 3 because 3 phases coexist. C is the number of chemically independent species. What does that mean? If you have only water in the system, C is 1. If you only have CO2 in the system, C is 1. If you have both water and oil in the system, now you have 2 chemically independent species. What if you have N2O4 and NO2 in the same system? Well, in this case, although there are 2 chemicals, but there's only 1 chemically independent species because there is a chemical equilibrium between these 2 chemicals. There is a equilibrium constant at a given temperature for the reaction between these 2 chemicals. So therefore we say among these 2 chemicals there is only 1 chemically independent species. We can prove the phase rule as follows. Let's say in each of the P coexisting phases we have C chemically independent species, and therefore we have C variable mole fractions because the sum of the mole fractions must be 1 in every single phase. The total number of variables regarding the mole fractions of all species in all phases is actually P times C minus 1. Again, for example, if you have 2 components in the liquid phase, well, and you have 2 mole fractions, 1 for each component, but these 2 mole fractions have a sum of 1. So if you know 1 mole fraction, you can determine the other mole fraction. Therefore, we need to use C minus 1 here. And again, you have C minus 1 variable mole fractions in each phase. And if we have P phases, the total number of variables regarding the mole fractions is P times C minus 1. And we also have 2 other variables, pressure and temperature. So we have a total number of P times C minus 1 plus 2 variables in total. And again, this lowercase p is the number of phases. C is the number of chemically independent species. Plus 2, these 2 come from pressure and temperature, 2 other variables. And now we're going to look at some relationships between those variables, because each chemical coexists in all P phases, and therefore at equilibrium its molar Gibbs energy of phase 1 should be equal to its molar Gibbs energy in phase 2, and also equal to the molar Gibbs energy of phase 3, etc. And there are a total of C times P minus 1 such equations. Why is that? For every single chemical, there are p phases. And then we can write p minus 1 equations that equate the molar Gibbs energy of all those phases. Again, it's p minus 1. And we have how many chemicals? We have C chemicals. Therefore, we can write out C times p minus 1 such equations. Each equation can reduce the degree of freedom by 1, or can reduce the number of independent variables by 1, and therefore the number of degree of freedom is this p times c minus 1 plus 2 over here. That's the total number of variables here, and then minus the number of equations that connect those variables, because each equation reduces the degree of freedom by 1, and we do this simple algebraic operation, we get c plus 2 minus p. That's the phase rule. And when there's only one chemical species, such as pure water or pure CO2, and then C is equal to 1, F equals 3 minus p. Because the number of degrees of freedom cannot be negative, so only up to 3 phases may coexist if you have only one chemical in the system. And when 3 phases coexist, we have a triple point. Again, there can be a triple point up to 3 phases coexist, and there's no way for us to have 4 different phases coexist in the phase diagram of only one chemical. Again, the phase rule states that in a phase diagram we have F equals C plus 2 minus P. F is the number of degrees of freedom, and C is the number of chemically independent species. So if you have water and vegetable oil, we have 2 independent species. Oh, sorry, this is not a good example because vegetable oil is not pure. So how about this? What if you have a mixture of water and cyclohexane, and then C equals 2, all right? But if you have N2O4 and NO2, in that case, well, there's only one independent, a chemically independent species. And also, what if you have 3 different gases? What if you have CO2, oxygen, and CO? It seems that you have 3 chemicals, O2, CO2, and CO, but among these 3 chemical species, there are only 2 independent, chemically independent species, because there's a chemical equilibrium among these 3 species. All right. And now let's look at this P. P is the number of coexisting phases. So in an area, for example, like this, we have only the gas phase, and we have 2 degrees of freedom, because you can change P and T at the same time independently. So we have 2 equals 1 plus 2 minus 1, and that's correct. Now if you look at the coexistence lines, alright, when you see a line, there's only 1 degree of freedom, so F equals 1. And since we have only one species, so it's just 1 equals 1 plus 2 minus P, and you can solve this equation, P is 2. And indeed, along any coexistence line, there are 2 phases. So along this line, you have liquid and gas phases. Along this line, you have solid and gas phases. Along this line, you have solid and gas phases. So again, this equation holds. At this triple point, we have 0 degrees of freedom. So F is 0, and then 0 is equal to 1 plus 3 minus P, and then P is 3. We have 3 phases at the triple point. And again, if you have a pure substance, there's no way for you to have 4 phases coexisting at a given temperature and pressure, because you can plug in the numbers. If you have only one species, C is 1. And if P is 4, you are looking at 1 plus 2 minus 4, -1. You have -1 degree of freedom, and that does not make any sense. So that's why if you have only one chemical, you can have up to 3 phases coexisting at a given pressure and temperature, and that's called triple point. So again, if there's only one chemical species, F is 3 minus P, the number of degrees of freedom is 2, 1, or 0 when 1, 2, or 3 phases coexist. This is just simple calculation over here. Now, if you have 2 chemically independent species, one example here is sodium and potassium. Another example is water and cyclohexane. They are chemically independent because there's no chemical equilibrium between sodium and potassium. There's no chemical equilibrium between water and cyclohexane. When that's the case, we have this C equals 2, since we have 2 chemically independent species, and F is 4 minus P. And in this case, if you have a mixture of sodium and potassium, it's possible for up to 4 phases coexist at a pressure and temperature. And in that case, it's called a quadruple point. It's called a quadruple point. 4 phases coexist.